for my Math 72, which is Calculus 2, on power series. So, try to review those, all right? Otherwise, you're going to get lost when we start chapter 6, all right? So there are a lot of things, and power series is not an easy chapter, okay? So during my time when I went to college, I think I shared with you my story about my hardest math professors who was Calculus 3, right? Okay, so that chapter was the only chapter that he tested on the final exam, okay, because it was hard, all right? So and that was the chapter that determined my future and my life, because I did very well on that chapter that he considered it was hard, and it was hard. And I said, well, if I could get an A in his class, and if I did well on that power series chapter, then I could do anything in math, right? So that was how confident I was after I finished his class. So I decided to switch my major from electrical engineering to applied math, okay? So with that said, I hope you will take it seriously and read my Calculus 2 lecture notes that I uploaded on Canvas. Now remember, I never share my complete notes with my students. I expect students to take notes just like you do. If you ask me for complete notes, I wouldn't give them to you, because I want you to take your own notes so you can read your own handwriting and learn more, all right? But because chapter 6 requires your knowledge of power series, and I don't know how good your notes were when you took notes for that class, or if you still have them. That's why I provided those notes for you, okay? So let's go to section 4.6 and finish up, and then we're gonna go to 4.7. Okay. All right, I made a note. So you see my notes? Kind of reminded myself to talk about exam 1B today. Okay, but because I'm a little bit behind, so let me do the lectures first. And just in case I run out of time to go over the test today, usually I can only go over a couple problems. But if I do not have time to go over today, I might post the solutions for you to read, okay? Instead. All right, so let's erase that. Okay, so where were we last time? Okay, so this was the example. Okay, so we were using variation of parameters to solve. Okay, and okay, so what? And then we got the U1 prime, right? So we got the U1 prime first. So now let's go ahead and find out what U sub 1 is, and then we're gonna find out what U sub 2 is. Okay, so here's my my virtual home button that I can use as a pointer. All right, so for this one right here, on the right-hand side, for this integral right here, you can use U substitution, because if you let U, okay, so by the way, when you have something like this, make sure you show work, okay? So I'm not gonna use U because we already use U's over here. So let's use something else. So let's say W, okay? So let W be 1 plus x squared. Okay, I wonder who that's still in.
We can't see anything being updated.
You cannot see my notes?
I can see your notes, but I didn't see anything change.
Right here, you see anything here?
Yes. Yeah, we see that.
Sorry.
Yeah, that's what
Oh,
I just
that
wrote.
was cut off. Sorry, that was cut off for me. My Zoom was cut off. Sorry.
Okay. Can you see it now?
Yeah.
Okay. Okay. So by the way, while I'm lecturing, if you see any student coming in the waiting room, please remind me. Okay. So right here you have that. So the derivative of W is 2x, and then you have dx over here, right? Okay. So you just go back here. So you have negative. So x dx is dw over 2. So I take 1/2 out, and then I have dw over w in here. So that gives me negative 1/2 ln of the absolute value of w, right? And then plus a constant, okay? So that turns out to be negative 1/2 ln of absolute value of 1 plus x squared plus c. But remember, we are only looking for a u1 and a u2, right? So right here, when we set this up, right, u1 and u2. So it's just like how we did it for integrating factors and also for reduction of order. So so in this case, we have many choices of u1, right? Because if you pick a different number for c, you get a different u1. So you always want to get the simplest one. So the simplest u1 would be letting c be what?
0.
Yeah, so you let it be 0. So let's see be 0 because you want to get the simplest u1. And then also, we know that this guy is always positive. So we don't need the absolute value, okay? So from here, u1 is equal to negative 1/2 ln of without the absolute value symbol, because 1 plus x squared is always positive. All right, so that's what we have for u1. Now, let's go ahead and find out what u2 is. So we're gonna find out what u2 is. By the way, let me see if I think there was a student in the waiting room, right? Let me see. Okay. Okay. Yeah, so I hope next time you guys come to class on time, because it's really disruptive when you come late, because I'm lecturing, and sometimes I don't want to stop in the middle of the lecture to switch back to the Zoom window to allow you to come in. All right. Okay, so u2 prime. So what is u2 prime? u2 prime. u2 prime. U sub 2 prime. The denominator is the same, right? But the numerator, right here, the numerator, you're gonna replace the column of u2 prime with the column of the constants, with the things on the right side. Okay. So in the numerator, the determinant is going to be e to the x for the first column, and then the second column is going to be 0 e to the x over 1 plus x squared. And
Professor,
the denominator is the same.
Can you see the message that was just posted?
Can I see the message?
Yeah. The person you just let in, he said that he was on time, but his computer crashed, so we had to rejoin.
Oh, okay.
Yeah.
Okay. Okay. So if that is the case, just remind me, especially before you leave today, okay? Because yeah. So yeah, for iPad Pro, when I lecture, then that Zoom window is gone. Okay, so I would know whether you were here or not on time. Okay, so let's go down here and write down u2 prime. So u2 prime is now, so in the numerator, you're gonna have e to the x, e to the x, and the coefficients of the e of u2 prime, you replace those with the ones on the right side of the equal sign. So you have this and this one. All right, and I'm going to rewrite the denominator again. So the denominator is e to the x, e to the x, x e to the x, and then x e to the x plus e to the x. And we already know what the denominator is. We found it up here, right? So it's right there. So it's e to the 2x. Okay, so when you go to the second function u2 here is faster, so e to the 2x. All right, now the numerator, if you cross multiply those two minus those two, so what you have is e to the 2x over 1 plus x squared. Okay, and then if you flip the bottom one over and multiply, then you have 1 over 1 plus e to the not e, is x squared, 1 plus x squared. All right, okay, so what we have is, so u sub 2 prime is equal to this. Okay, so what is u sub 2? U sub 2 is the integral of this, which turns out to be tangent inverse of x plus a constant. And then we want this constant to be 0 so we can get the simplest function u2, right? So let's see the 0, okay? So u sub 2 is equal to tangent inverse of x. All right, so what is your yp? So yp, the particular solution is u1 y1 plus u2 y2, right? So let's write down. Okay, so thus you write down the indentation. Okay, so yp is equal to u1 y1 plus u2 y2. Okay, so that implies y sub p is u1, which is negative 1/2. I remember ln right here, right here. Okay, times y1, and y1 is e to the x, plus u sub 2 is tangent inverse of x, and y sub 2 is x e to the x. Okay, so what is the general solution is y equals y sub c plus y sub p, where y sub c is what? Is c sub 1 e to the x plus c sub 2 x e to the x plus y sub p. Remember, y sub p should never contain a constant, okay? Because y sub p means a particular solution, right? So for particular solutions, you don't have constants, c, but y sub c, you do have constants, okay? So here, so if you simplify this one, you can just multiply e to the x to the negative 1/2. So you have basically minus e to the x over 2 ln of 1 plus x squared. Okay, and then plus x x e to the x tangent inverse of x. All right. Okay. So how are you going to set up for a third order differential equation? Okay, so I'm going to set it up, but I'm not going to do the prompt, so you can see how. Okay. So
Sorry,
I went
can you
over.
scroll up for a second?
Yes, right here.
A bit more. Yeah, right there. Thank you. Got it.
Okay. So now, if I give you a third order differential equation like this, remember, like right here, it is a 1, right? It is a 1, which is good. Right. So that's what you want. That's a 1. So that's good enough. So the first thing you do, because this is a third order, right? So your y sub c is going to be c1 y1 plus c2 y2 plus c3 y3. So there should be 3 solutions for y sub c. So you know y sub p is going to be what? Y sub p is going to be u1 times y1 plus u2 times y2 plus u3 times y3. All right. So this is what I need you to set up before you get to the determinants. So because it is a third order, you need a system of 3 equations with the u's in there. So the way it is what? So the first row is y1 u1 prime plus y2 u2 prime plus y3 u3 prime equals 0. Now the second equation also has equals 0, and the third equation is going to be the function on the right, which is f of x. So this is what I need you to show. Okay. So I know that you understand how variation of parameters method works. Now the second row is going to be u1 prime, u1 prime, y1 prime, u1 prime, y2 prime, u2 prime, and then y3 prime, u3 prime. Okay, and the third row is going to be y1 double prime, u1 prime, plus y2 double prime, u2 prime, plus y3 double prime, u3 prime. Okay, so the way to set up is let me highlight the coefficients of the u1 prime and the u1 prime, u2 prime, and u3 prime, so you know how to get the determinants. Because if you have color markers, you can color code everything, and it's easier for you to see things. So here is what you have. So you have this one of them right here, right? So that one right there. Okay, and then the next one is this one. Okay, what the next column I'm going to use is this one. Okay, wow. And then the one on the right is this one. Okay, so in the denominator of these 3 u primes, you should have a 3x3 determinant of the 3 columns on the left side, right? So you have on the bottom. Okay, so you're gonna have y1 prime, y1 double prime, and then y2 prime, y2 double prime, and then y3 prime, y3 double prime. And then you have, it's the same, okay? So the same for all 3 of them in the denominator. Okay, so down here, I'll just say the same as this one. Okay, and the same here, right? The same for all three. Okay. Now in the numerator, for U1 prime, you're going to replace this column with the yellow column on the right, right? So you're going to have 0. Let's say, so we're going to have this. So 0, 0, f of x, and in the middle you have y2 prime, y2 double prime, and on the right you have y3 prime, y3 double prime. Okay, so I hope you remember how to get the values for the determinants. Okay, so if you don't remember, you need to review, okay, on your own. So the middle column for the middle for the numerator of u sub 2 prime, then you just replace the coefficient column of u2 prime with the column on the right. Okay, so basically, so you have, so in the middle you're going to replace that with this, and then on the left you have y1 prime, y1 double prime, and on the right you have y3 prime, y3 double prime. Okay, and then for u sub 3, you just replace the column of u sub 3 with the column on the right, so you have that. Okay, and here you have y1 prime, keep writing y1 double prime, and then y2 prime, y2 double prime. Okay, so you just simplify, evaluate this determinant and this determinant, and then simplify the quotient, and then take the integral to get u1, and do the same thing for u2 and u3. So the process is longer. Okay, but you know, if you understand how the variation of parameter methods works for a second order differential equation, then for higher orders it's the same thing, but it takes longer because you have more things to work with. Okay, unless you don't remember how to expand a determinant, right? Okay. Okay, so that is 4.6. Now let's go to 4.7. So 4.7, we're gonna learn how to learn how to solve a special differential equations. So we have a special name, and you will see how special that is when I switch to that. Okay, so here is 4.7. Oh no. Okay, I thought I lost the lecture notes. Okay. All right. So in this case, we're going to learn how to solve Cauchy-Euler differential equations. Okay. So I have to, when I do this, let me see if I can see you. I remember when, just to share with you, I remember when I was at UC Riverside for my graduate school, I had a lot of stress because, you know, like no social life, just studying, learning. So I got a lot of stress. So my landlord allowed me to have a little puppy, right? So she suggested me to get a puppy to help me with that, right? So I bought a puppy, and I didn't know what to name the puppy, right? So, and at the time I was learning advanced calculus. Okay, so when you major in math, for your bachelor degree program, you have to take advanced calculus. That means you have to prove all the theorems that you learned in your basic calculus, like the mean value theorem. Everything in the theorems you have to prove, right? Like the theorems in differential equations here in this class. When you go to the next level of differential equations, you need to prove those theorems, right? And then this class that I take at the time was advanced calculus, which means this is the advanced calculus in graduate school, in graduate program. So when I bought the puppy, and at the time we were learning Cauchy, right? Cauchy theorem. So I didn't know what to name the puppy. So I said, okay, let's name him Puppy, Cauchy, right? So I just call him Cauchy. So that I remember that all the time. So the first puppy that I had was Cauchy. Okay, so now you see Cauchy and this is Cauchy-Euler differential equations, because Mr. Cauchy and Mr. Euler together came up with this stuff. Okay, so they named this type of differential equations Cauchy-Euler equation. Okay, so what is that about? Well, so let's go over this stuff. So prior to this section, we learned how to solve differential equations of this type where the coefficients are constants, right? So they are all constants. Okay. Now in this section, we're going to introduce something to this differential equation. That is, if you have like a first derivative, then we're going to multiply that term by x to the first. If you have second derivative, we multiply that term x squared. Okay, so for each term, we're going to multiply by x raised to a power that matches the order of the derivative. Okay, so right here, there's no derivative, which means the order of the derivative is 0. So you multiply x to the 0 power, which is 1. Okay, so that is very easy to understand. Okay, so this one right here, this equation, okay, we call it a Cauchy-Euler equation. Okay, so when you have a differential equation where the independent variable is raised to a power that matches the order of the derivative for that term, then we know that that is a Cauchy-Euler differential equation. Okay, all right. So now, how are we going to solve Cauchy-Euler differential equations? Okay, so let's look at the simplest Cauchy-Euler equation first. And by the way, when they say Cauchy-Euler, I mean Cauchy. When they say Cauchy-Euler equation, I mean Cauchy-Euler differential equation. Okay, so here is a simple Cauchy-Euler differential equation, which is a second order, right? Now this is still linear. Okay, remember by definition, a linear differential equation is when the dependent variable y and all of its derivatives are raised to the first power. So this is a linear second order Cauchy-Euler differential equation. That's what it is. All right. So here are some more examples. So this is a linear fourth order, because it's fourth derivative, fourth order and Cauchy-Euler equation, because you see each term there is a factor of x raised to a power that matches the power of matches the order of the derivatives. Okay, and here is another Cauchy-Euler differential equation. All right, so I hope you can recognize Cauchy-Euler equations when you see one. Okay, so now, so this is what these two mathematicians did. Okay, so of course they did something which you're gonna see toward the end of this section, this lecture, and then when they did that, then they discover something, right? They discover that a solution of a Cauchy-Euler equation has to form x to the mth power. Okay, and you will see why when we get to the last problem in this section. All right, but so just like prior to this section, the complementary the homogeneous differential equations has solution of the form y equals e to the mx, right? For Cauchy-Euler, it is just x to the mth. Okay. So what we need to do is we need to find out what m is, so we can get the solution. Okay. So before we do that, so here we know that the solution, its solution has this form, and we want to know how to get the m. So we need to plug in the y prime and y double prime. So in order to do that, we need to find out the first and the second derivatives of this one. Remember, m is a constant, so the derivative of x to the mth is going to be m times x to the m minus 1. Okay. And then for y double prime, which is the derivative of y prime, so the derivative of this is going to be m times the factor of m minus 1 times x raised to the power m minus 1 less 1, right, which is m minus 2. So that's for calculus 1. All right, so those are the two derivatives. So now let's plug them in. Okay, remember we name, so this is the second order differential equations, right? So that is a non-homogeneous differential equation, remember? So in order for you to be able to find the general solution of this one, first you have to find out what the complementary solution is, and then you have to find out what the particular solution is, and you add them up, you get the general solution. Okay, so this is what we're going to do. We're going to find out the complementary solution, and the complementary solution is the solution of the associated homogeneous differential equation of that non-homogeneous differential equation. So you see, I use a lot of differential equations language, and you need to understand what I just said, right? And you know, so that's all of that stuff is from section 4.1, basically. So all right, so let's plug them in. So for the first one, I have a x squared and y double prime. Y double prime is m minus 1 x m minus 2. Okay, and then plus bx times y prime, which is m x to the m minus 1, plus c. Now this is a small c, okay, not the capital letter C that you use for your constants in your general solution. All right, okay, so y is what is y? Y is x to the mth. So y is x to the mth. So I'm going to use okay. Remember, this is similar to what we did for in section 4.3, I believe 4.3, to get the m values, or to get the auxiliary equation for the associated homogeneous equation. So here we're gonna try to get the auxiliary equation for this Cauchy-Euler homogeneous equation. Okay. So let's see what we have. So we're going to simplify, right? So when you multiply out, you see the x squared times the x to the m minus 2, that's going to be x to the mth. And so that's the reason why, okay, when you do this, then x times that is going to be x to the mth, and you have x to the mth. So all of them will have x to the mth factor. So you have a m minus 1 x to the nth. All right, so let me just move that a little bit over here so you can see. So that is from the first term. Okay, and then the second term, if you multiply out, you're gonna have b m, x to the mth. And then this one is c, x to the mth. All right, and now you see that all of them have x to the mth in common. You want to factor out x to the mth. So you get a, m, m minus 1, plus b, m, plus c. Okay, so if you have a product, so you have a product, which is this one times that one, and you get 0. So you know that either that is 0 or this is 0. Okay. Now, but of course, x to the mth cannot be 0, because if x to the mth was 0, then y is equal to 0, which is a trivial solution. That's easy for you to check on any differential equation. So if I give you a differential equation, you can check whether y equals 0 is a solution, right? It's easy. So, you know, a non-trivial solution is what we are more interested in, because a trivial solution is easy for us to find, okay? So that's why we don't want this to be 0. So that means this has to be 0, okay? So that implies this equation. And this is what I need you to know, okay? So please do not memorize the formula in the book, okay? Because in the book, that formula, you know, I don't want you to rely on your memory, okay? Which is not good. And I can show you an easy way of figuring out what the auxiliary equation is for a Cauchy Euler. So I think there's a formula in here that I do not. I think I made a note. Yeah, like this one right here. This one that I black out. Okay, so, let's see what that is. Okay. Okay, see right here. You know, don't do this, because then you rely on memorizing this. Just know this, and I will show you how to figure out that one. So let me just black that out, and let me go back to the lecture notes and I'll show you. It's very easy to tell. So you know that. Okay, let's write this down first. Okay, so this equation is called the auxiliary equation of that homogeneous differential equation, okay, which is double star, right? So I use, okay. Okay, so how do you figure that out? So let's use this. Okay, ready? So you know that each term here has A, B, and C, right? Whatever they are. So you have A, B, and C. So for the term containing A, how do you know that this is M and M minus 1? Well, because that is Y double prime. What is Y double prime? Y double prime is M, M minus 2. And you know that when you have x squared times that, it's going to give you x to the mth, right? And you factor out. So that's how you figure out. And then Y prime has M. You see, because when you take the derivative of x to the mth, you get M. Okay. So if you had a third order, what would it be over here for that first term? The coefficient, whatever the coefficient is, times what? If there was a constant times x cubed, y cubed, then what should be over here? It would be the constant, whatever the coefficient is, times m minus 1, m minus 2, because when you find y triple prime, you have m minus 1, m minus 2, right? Okay, right here. So let's do that. The next one. So for the first term, what do you have? You have a. Okay. So the y triple prime, so just remember the y triple prime is m minus 1, m minus 2, right? Times x to the m minus 3, okay? And then x to the m minus 3 times x cubed is just x to the mth. Okay, and then you know all of these will have x to the mth in common when you factor out, and you know that that cannot be 0. So the